function. I've actually never heard anyone mention it, but there's no mean line reality.
It's really from one side, from open side to the
Okay.
Okay, welcome back to the last afternoon of the talk, and the first up this afternoon is Claudia Rella from University of Geneva, who's going to talk on Stokes constants in topological string theory.
Thank you. So I'll start by thanking the organizers for giving me the opportunity to talk. And I'll present today some work that have been doing recently, and it's not yet on the archive, but it will appear soon. I'm going to start with some motivations and some background. Okay. So this project concerns enumerative invariance and resurgence together. It's been motivated by a series of studies that have emerged recently that have tried to reframe enumerative invariance based on the counting of BPS states in a more analytic framework, which is the framework of resurgence. And all of these recent works that I put here on the slides concern in particular theories that are controlled by quantum curves in exponentiated variables. And it's been conjectured that the relationship between enumerative invariance and Stokes constants from resurgence and particular structures of singularities in the Borel plane known as Peacock patterns are typical of this kind of quantum and string theories. So the objects of interest will be asymptotic resurgence series that arise as perturbative expansions in some appropriate scaling limit in a quantum theory. And resurgence gave us tools to unveil a whole structure of non-perturbative corrections, exponential type non-analytic corrections to these perturbative expansions, and canonically associate to these non-perturbative sectors some numerical data known as Stokes constants. And in the cases that I write here in this very recent papers, it's been found in some concrete examples, but conjecture in general, that Stokes constants that arise from considering particular perturbative expansions have indeed a quite concrete interpretation in terms of BPS invariance. The last one of these papers presents this formalism in the context of topological string theory on a Calabi-Yau threefold, and in particular in the weakly coupled regime of the topological string. So I will tell you about the dual story, the dual picture that arises in topological string theory in a CY threefold when instead of looking at the weakly coupled regime, we look at the strong coupling in an appropriate way that I'll tell you about shortly. Before I'll give you a little bit of background on the physical side, and in particular on the connection between topological string theories and the spectral theory of quantum mechanical operators. This is a two-way connection, and one can look at one side of it and go from topological strings on a toric Calabi-Yau threefold to quantum operators and the other way around. This is, however, a conjectural correspondence. So one side of it is built on quantization and mirror symmetry. Local mirror symmetry pairs a toric CY threefold with an appropriately defined algebraic curve of a given genus. And the quantization of this algebraic curve leads to quantum mechanical operators on the real line, one for each integer up to the genus. These have been conjectured to be positive, definite, and of trace class under some mild assumptions on the mass parameters of the CY. And they've been proven to be so in a series of concrete examples. Because we assume this to be true, we can define the Fredholm determinant of these trace class operators, and this is going to be an entire function of the complex deformation parameters of the CY, which I denote kappa. And the fermionic spectral traces of these quantum operators arise as coefficients in a local expansion around the orbifold point of the geometry of the moduli space of the CY. Now, these are, by construction, analytic functions in real positive H bar, but for our purposes, we will need to work with the complex Planck constant, and we will assume that it's going to be possible to analytically continue H bar, although it's always going to be verifiable in examples. So the other side of the story is what is properly known as topological strings spectral theory correspondence. And this is a conjectural correspondence which gives an expression for the fermionic spectral traces in terms of the total ground potential of the topological string theory on the Calabi-Yau. So I put here the integral formula that gives the fermionic spectral traces, and here you see this depend on integers which are collected in the vector n and on the mass parameters and on the Planck constant H bar. On the other side, this integral transform, which can be interpreted as a Fourier Laplace transform, a symplectic transformation in moduli space, includes this total ground potential J, which is a function of the chemical potential, equivalently the true complex moduli of the CY, again, the mass parameters and the Planck constant. I mentioned that the Planck constant that arises in both sides of this equation has a different origin, but it's identified. So on one side, from the fermionic spectral traces side, we introduce the Planck constant as a quantum deformation parameter. On the other side, this coupling H bar, which appears in the total ground potential, is arising from this necklace of Saakashvili limit of the refined topological string as a proper string coupling. So the total ground potential can be written as the sum of two contributions, which capture two different limits, specializations of the refined topological string. And they are the worldsheet instanton ground potential and the WKB ground potential, which correspond to the standard or unrefined and the NS topological strings. Now, in this context, there is a strong weak coupling duality between the standard coupling GS of the topological string and the quantum deformation parameter H bar. And we will often refer to the scaling limits in one or the other of the two couplings, keeping in mind this duality. Now, this is more or less the physical context we will work on, and I'm going to give you a bit of notions from the theory of resurgence, which will be the building blocks of this work. And I will start by introducing a generic resurgent Givray-1 asymptotic series as the many perturbative expansions that we will meet in quantum theories. This phi of z with a factorial growth of the coefficients. And one can perform the Borel resummation of this Givray-1 asymptotic series, as we know, by this two-step process. First, moving from the phi z to its Borel transform, and then by the Laplace transform, formal inverse of the Borel transform, resumming the original series along a given ray in complex plane, which I denote rho theta, theta being the direction of the ray. Now, this process of Borel resummation will give us a locally analytic function in the complex z plane everywhere except where the Borel transform of the series has a so-called Stokes ray. So along the directions which are identified by the singularities of the Borel transform in the Borel plane. The Borel resummation will have discontinuous jumps when this angle of resummation crosses the direction of a Stokes ray. Here, omega labels the singularities, zeta omega of the Borel transform. So we will ask, what can we understand from measuring this discontinuous jump of the Borel resummation of the resurgent series? So the discontinuity across the Stokes ray is defined as the difference in the Borel resummations along two rays that are slightly above and slightly below a Stokes ray. And a simple contour deformation argument shows that this difference is given by a sum of contributions which come from each one of the singularities along the Stokes ray. And each of these contributions is an exponential type non-analytic correction, as you see in the formula. And it brings with it a numerical data, this S omega, which is the Stokes constant at the singularity, zeta omega, and another resurgent Givray-1 asymptotic series phi omega. Now, these two elements that encode the non-perturbative contribution given by each of the singularities are themselves encoded in the local expansion of the Borel transform at the singularity itself in the Borel plane. And we can see this in an example if the singularity is a logarithmic branch cut, as it will often be the case in quantum theories and in topological string theories in particular. The local expansion of the Borel transform as the form in the slide. So it gives the Stokes constant times a logarithm in the difference, zeta minus zeta omega, times the Borel transform of the same series that appears in the discontinuity plus regular terms. The Stokes automorphism is a formal operator that depends crucially on the choice of direction, as do the lateral Borel resummations, and is defined as the convolution of the Borel resummations above and below the ray. Now, this procedure that brought us from phi to this collection of elements, phi omega, S omega, asymptotic series, and numerical data, can be repeated with each of the series in the set. And it will give us new asymptotic series and new Stokes constants. Now, each resurgent series in this process can be promoted to what we call a basic Tron series. We put together the asymptotic series and the exponential type correction associated to it into one non-perturbative object, which is the basic Tron series. Now, this process we have described brings us from an initial formal power series to a whole family of them and carries with it the definition of the Stokes constant. And we define then the minimal resurgent structure associated to the original perturbative power series as a subset of this family that is constructible, and precisely as the smallest subset that is closed under Stokes orthomorphisms. There are particular configurations of the singularities in the Borel plane of perturbative series that appear in quantum theories. There's, in particular, the configuration of peacock patterns of singularities in the Borel plane, which is expected in theories based on quantum curves as topological string theory. And it's a particularly symmetric periodic configuration of singularities, where we have a finite number of vertical lines in the Borel plane along which the singularities sit, repeated at integer multiples of some constant. And it's the pattern of the corresponding Stokes rays that gives the name to it. Now, this was the background. I am going to apply this to the context of topological string theory, and this is based on a paper to appear soon. Let me start getting more concrete on which objects in the context of topological string theories I'm interested in. So we consider the semi-classical limit of the dual spectral theory of topological strings. So the limit h bar going to 0 in the spectral problem, which arises from the quantization of the mirror curve to the Cy, as I recalled at the beginning. So in the strong weak coupling duality I mentioned, this will correspond to the standard topological string coupling constant GS going to infinity. So the fermionic spectral traces Zn h bar, I drop the dependence on the mass parameters, can be expanded perturbatively around h bar going to 0. And according to the same mechanism I described in generality, it will produce a full family of asymptotic series, which will be indexed by the same set of non-negative integers n, and which are expected to be Givray-1 and resurgent. And these assumptions will be verified in examples. Now, some explicit results obtained studying the first resurgent structures of two simple examples of toric Calabi-Yau threefolds, which are local P2 and local F0, suggest that the peacock pattern configuration of Stokes rays in the Borel plane is a typical characteristic of this setting. And in particular, we can get more precise. The kind of peacock pattern configuration that is suggested by the examples is a particularly periodic, regular one. So I can describe it by a family of finite members of give rate 1 asymptotic series, which I call phi sigma n of h bar. So this parameter sigma from 0 to some finite positive integer L, depending on the n and on the CY geometry, is basically selecting a vertical line in the Borel plane. And the case of sigma equal to 0 will be our original perturbative expansion. Now, for each sigma, then we associate to this single asymptotic series an infinite family of basic trans series. So the phi sigma n of h bar is multiplied by this exponentially small subleading correction in h bar, which introduces an extra index, the integer n, and this constant a, which appears in the exponential, is a complex number which depends again on the geometry and on n, but it does not depend on sigma. Now, this basic trans series that are described in this way capture a whole structure of additional invisible sectors of the topological string theory, or equivalently of the spectral theory. And we can put them together into this minimal resurgent structure that I defined previously. And as I told you before, in the general picture from the minimal resurgent structure, then we can build this. We can decode this infinite collection of Stokes constants, which depend on two indices, sigma, and on the integer n. And this is due to the particular form of the basic trans series in this minimal resurgent structure. Now, we expect this to be rational numbers after choosing an appropriate normalization of the asymptotic series. In the dual limit of GS going to 0 or h bar going to infinity, the same resurgent machine, as it was called by Gu and Marino in the recent paper, is applied in this opposite scaling regime. And in the same fashion, from the fermionic spectral traces, they produce a family of factorially divergent formal power series. They verify numerically in examples and then conjecture generally that this series lead to some particularly symmetric peacock patterns of singularities. And in that case, the collection of Stokes constants are the Stokes constants in the collection, they're conjectured to be integers. Now we can look at these two dual scaling regimes on the topological string side or on the spectral theory side and compare the pictures. So I just told you how to use this resurgent machine of Guin-Marino in the semi-classical limit H bar of the dual quantum mechanical spectral theory. And schematically, this brought us from this collection of original perturbative asymptotic series to the set of Stokes constants, infinitely many and expected to be rationals. The same thing is done in the tensionless limit of the string in the paper by Guin-Marino, and it.
Why do you call this limit tensionless? The alpha prime to infinity tensionless. Yes to 0 usually is not tensionless.
Maybe it's not standard nomenclature. It's the small radius regime of the conventional topological string, more the weak coupling regime of the yes. So what are the similarities of the two constructions? Well, first of all, the Stokes constants are expected to have some sort of interpretation in terms of enumerative invariance of the underlying theory, although a clear geometric and physical identification is not yet understood, contrary to the previous examples of supersymmetric H theories and complex Chern-Simons theories, where the same idea is brought to very concrete identifications with the BPS invariance or the DGG index in the case of complex Chern-Simons. The Stokes data represent a collection of numbers that are uniquely determined by the original perturbative expansion, but they are, in their construction, non-perturbative. In both limits, in both constructions, computations in the examples rely on the TSST correspondence that I recalled at the beginning. So they will resort to the explicit expressions for the fermionic spectral traces. There are also some differences. So as I will show you in a concrete example, the Stokes constants are not necessarily integer numbers in the case h bar going to 0. Although it is possible in the examples that I have studied to relate them to some non-trivial integer sequences quite easily. Also, the asymptotic series that resurge from the initial perturbative expansion in the case of GS going to 0 possess this exponential factor of the form 1 over GS, which is related to the conifold volume conjecture of toric Calabi-Yaus. Explicit computations in our limit h bar going to 0 show that this exponential factor does not appear. So I will focus on a very concrete examples which makes a lot of this conjectural statements manifest and much more concrete. And this is the example of loco P2. A quick introduction to the loco P2 geometry. So this is a very simple example of toric CY threefold, is a toric del pezzo CY threefold, meaning its genus is 1. So it has one complex modulus and it has no mass parameters in particular. It is defined as the total space of the canonical bundle on P2. And thanks to the TSST correspondence, we can resort to this formula for the fermionic spectral traces in terms of matrix integrals. In particular, I will focus on the first fermionic spectral trace. So this matrix integral representation comes from writing the fermionic spectral trace in terms of a determinant integral using the integral kernels of the quantum operators, which arises from the quantization of the mirror curve. Here, phi b is Faddeus quantum dilogarithm, which plays a crucial role in actual computations. So we want to study the first resurgent structure, Z1 H bar. So the first approach is a purely numerical resurgence study. We can expand the integrand of the previous formula in the limit where b goes to 0, which corresponds to H bar going to 0. Integrate order by order in B. And this allows us to compute numerically the perturbative series to very high order. And as you can see in this example, there's no exponential prefactor. There's a 1 over H bar prefactor and a perturbative series of alternating sign in even powers of H bar. So a numerical analysis of this perturbative series with the tools of resurgence shows that, well, the coefficient, first of all, have the expected factorial growth, and we can identify this constant Hey to the precise number in the slide. And we can then apply the tools of Borel analysis and the additional help of conformal maps to study the pattern of singularities of the Borel transform in the Borel plane. So here I show you some pictures which, using the Borel analysis with various supplements, allows us to visualize the presence of the singularities in the Borel plane. Here the red dots in the first two plots are the actual singularities, and the gray dots are just spurious poles of the Padé approximant that are mimicking branch cuts. And these are indeed, as we will see later, logarithmic branch cuts. The picture above is using the technique of the test charge to show the presence of the singularities when they are hidden one behind the logarithmic branch of the other. So in particular, I am showing you just the upper half plane, but there are two dominant complex conjugate branch points, A and A star, and they're repeated at integer multiples along the imaginary axis. So it's a very simple peacock pattern. So we want to go on from in this resurgent machine, and from the pattern of the singularities derive and the original perturbative series derive the perturbative expansion around the first instanton section. So this phi 1 of H bar. We have a functional ansatz, which is very standard, and apply the standard large order relations for the perturbative coefficients. And these are used to systematically extract the values of A, B, and Bn in the functional ansatz. So first of all, we get confirmation that the functional ansatz is correct from this numerical study. And then we actually obtain the very accurate numerical estimates for all of these parameters. And what we find is that this first resurgent series, phi 1 of h bar, is actually proportional to the perturbative series we started with, phi of h bar. And there's just this proportionality factor 3 square root of 3i times the exponential correction in h bar. And S1 here is the Stokes constant associated to the dominant singularity. Now, we can do the same study in the case of local P2, but resorting to analytic tools. And this is because the local P2 geometry is quite special somehow, because the first fermionic spectral trace has a known explicit closed formula due to Kashiev and Marino. And we can expand it to all orders in h bar. Now, if we consider the series in the exponent, so not the full exponentiated series, but the eta of h bar is the series in the exponent above. So by application of Adam-Art's multiplication theorem, I am able to find a formula for the Borel transform n hat of zeta, which is an exact function of zeta, which I am not writing here because it's quite complicated, but it shows exactly that this Borel transform has logarithmic branch points at the points zeta, which are integer multiples of 4 pi I over 3. Well, not the 0. And we obtain the Stokes constants analytically from the local expansions of this Borel transform around the singularities. We obtain a very simple behavior, as we expect. So the local expansion of this Borel transform gives us the Stokes constant at the singularity and a simple logarithmic factor. And there are, so the corresponding resurgent asymptotic series is constant. So we have no perturbative contribution. And we can write then the first resurgent series as S1 times the exponential correction only. Now, quite nicely, the Stokes constant can be written in this form. They are, so if we factor out the first Stokes constant, which is this 3 square root of 3i, then the mth Stokes constant is going to be given by an integer number over the index m. And these integer numbers change sign with m, so they are symmetric up to the change of sign in the upper and lower plane. And we know them explicitly, we know them analytically exactly. And these results can then be cross-checked numerically via the large order asymptotics and the lateral Borel resumations that I recalled at the beginning, this time performing the numerical resurgent analysis with the series in the exponent of this exponential expression for the fermionic spectral trace. The next step is to translate this solution, which is for the series in the exponent, to the fully exponentiated series we started with, which is our original perturbative series coming from the fermionic spectral traces. And we can simply do this by applying the Stokes automorphism written in terms of alien derivatives. And we find an analytic solution to the resurgent structure of the original perturbative series, which confirms the partial numerical analysis we have done at the beginning and gives us much more information. In particular, from this, we can see that even choosing appropriate normalization, these Stokes constants are not integers. Now, the same analytic procedure I present here for the h bar going to infinity limit is applied straightforwardly to the dual limit. And I'll be very quick with this because it's exactly the same process. So we start with the perturbative expansion, but we don't look at the exponentiated series. We look at the series in the exponent in this weakly coupled limit, gs going to 0. We apply Adamard's multiplication theorem. We get a fully analytic resurgent structure and all of the information we might want to know. The Stokes constant have a very similar behavior, except for the pattern of signs. They're symmetric. And we can exponentiate via alien calculus, and this time we can verify the numerical estimates of Gu and Marignan. And we can see that in this limit, after the exponentiation, the Stokes constants are indeed integers. Now I'm gonna just tell you very quickly about some formulae. I'm not gonna get into the details of this. The message I want to leave you is that thanks to this analytic approach to low copy 2, the Stokes constant can be studied exactly, and they are available to somewhat arithmetic number theoretic investigation. And I've been able to find and prove this arithmetic formula for the Stokes constant in both limits, which somehow bridge to divisor functions, and the second two lines are quite just reformulation of the first, but under different terms. So the second kind of formula is providing us for a generating function for this integers am. The last line of formulae are multiplicative descriptions. We can find even more exact formulae, and this time they are explicit generating functions in the form of Q series for both limits. And from this formula, you can see the duality and symmetry of the two scaling regimes quite explicitly. I'm just going to stress that the generating function of this Stokes constants come from the holomorphic and anti-holomorphic block the composition of the fermionic spectral trace, as in the formulae. And the very last, there is an additional set of explicit number theoretic formulae in terms of Riemann zeta functions. And this, in particular, give us another perspective. These formulae can be interpreted as exact expressions for the large order asymptotics of the perturbative coefficients in terms of Riemann zeta functions. So I'm going to stop here. I will just tell you that this same construction in the general framework is also applied to the case a bit more complicated of the local F0 geometry, which is not accessible analytically yet, so only numerically, and it will also be described in the same paper to appear soon. Of course, we would like to have more information about the geometric and physical meaning of this constants, and that will be goals for future work. And thank you very much for your attention.
Thank you. Okay, we're running over a bit, so maybe we could save the questions until the tea break. So let's go straight into Diego, the next talk.